Hi everyone, welcome back to my channel. We'll explore a highly popular graph traversal algorithm that is the breadth first search. Now this is a very cool algorithm and it has a lot of real life applications. For instance, in maps or GPS systems, BFS or breadth first search can be used to find the shortest path or directions between two locations, especially in scenarios where the roads or connections form a graph-like structure. Here is a directed graph where node A has three neighbors B, C, and D. Each one of those three neighbors is connected to one node, which is E, F, and G, and they're all connected to H. Let's take a higher level view of what a breadth first search looks like. We can start at any arbitrary node. Let's pick node A. The first thing we do is explore all its neighbors. After that, the traversal moves on to the next level or layer of neighbors till it reaches the end. The traversal in the case of breadth first search is layer by layer, or you could say level by level. Whereas the other graph exploration algorithm, which is the depth first search, explores as deeply as possible along each path before backtracking to explore other paths. Please also make sure to check out my video in the algorithms playlist where I have explained the depth first search algorithm in detail. Now, breadth first search is implemented using a queue data structure. Let's step through the algorithm and see what the traversal looks like. Here is another graph where we will observe the progression of the breadth first search algorithm. Initially, all nodes within the graph are shaded gray, denoting their undiscovered status. A node is considered discovered upon its first encounter during the search, whereby the node color changes to orange. Upon discovering all its neighboring nodes, the node's color transitions to green to indicate that the node has been explored. We will be using a queue data structure to do the breadth first search traversal. We will add a node to the queue only if its color is gray. We can start the traversal from any node. Let's start with node B and we'll add that to the queue and mark it as discovered. Now, which nodes are its neighbors? These are nodes D and A. So we'll pop node B from the queue, mark it as explored, and append nodes D and A to the queue. The next node in the queue is node D. It has two neighbors E and F. So we'll pop node D from the queue, mark it as explored, and append nodes E and F to the queue. The next node in the queue is node A. It has one neighbor, which is node C. We'll pop node A off the queue, mark it as explored, and append node C to the queue. The next node in the queue is node E. It has one neighbor, node F, but node F is already discovered as it exists in the queue. So we will skip navigating to it. We'll pop node E from the queue and mark it as explored. The next node in the queue is node F. F has no undiscovered neighbors, so we'll pop that off the queue and mark it as explored. The last undiscovered element in the queue is node C. C does not have any neighbors, and we'll pop that off the queue and mark it as explored. Our queue is now empty. And with that, we have completed our breadth first search algorithm. We essentially use the queue data structure to explore nodes by proximity. This helps us with the traversal in the graph layer by layer. Given that this is an unweighted graph, which means the cost of every connection is the same, you are guaranteed that once you find the node, it is the shortest distance from the source. It's time to review the sample code for BFS. But before we do that, can I please request that you give this video a thumbs up if you like this video, and also please subscribe to my channel. If there are any topics you would like me to cover, or if you have any feedback, please leave a comment in the comments section. I would really appreciate it. Thank you. So this graph here can be represented as an adjacency list where each node is a key and its value is a list of neighbors. If you'd like a refresher on the graph data structure and its various representations, please be sure to check out my video on it, which I have linked to in the description. So the function breadth first search accepts two arguments. The first one called graph, which is an adjacency list, and the second one is the source node from where to start the traversal. Let's review the rest of the code. First off, I have declared a few variables. The first one is a queue that will help us in the traversal. The second one is a set called explored to keep track of the nodes we have discovered or explored. It will prevent us from navigating to the same node multiple times and will avoid the formation of a cycle. This is no different than coloring the nodes orange or green. That was done for pictorial representation and understanding of where we are in the traversal process. Finally, a list called output captures all the nodes as we traverse level by level. We'll add the source node to the queue and the explored set. We loop while we have elements in the queue. We'll first get the length of the queue at its current state, and that will aid us in traversing level by level. For the length of the queue, we'll pop the node and append it to the output so we can print it later. For each neighbor of that node, if that neighbor has not already been explored, we'll append it to the queue and add it to the explored set. Finally, we print the output that contains all the node we have explored in the graph. I have included a GitHub link to this code in the description. Please do try it out when you have some time. The code here works for both directed and undirected graphs that are unweighted. That means the cost of navigating to all connections is the same. You can use breadth first search to traverse a weighted graph also, and the underlying concept is the same. The implementation is a little different because it uses a priority queue and it's called Dijkstra's algorithm. Please refer to the playlist for a detailed walkthrough of that one. Let's go over the time and space complexity. The time complexity of BFS is O of V plus E, where V represents the number of vertices or nodes and E represents the number of edges or connections in the graph. That's because we are traversing all the nodes and edges. The space complexity is O of V. So that's it for this video. I hope this was helpful. I look forward to seeing you in my next video. Thank you and goodbye.